It's really a great pleasure and honor really to open this event, which is, as we know, the 25th, believe it or not, school for advanced studies in economics, economic theory. I think it's all said here. Really, it's a unique opportunity, first of all, to see that many months and weeks of works is kind of crystallized to one moment in which everybody is sitting, and then this is the first moment for you, but for many of us, mainly the staff and all the people that are around, it's the first time they can relax, and that's a good sign, which means that from now on, it's not our responsibility anymore. It's your responsibility to enjoy what we prepared for you, to enjoy the science, to enjoy the unique opportunity of a very, very fascinating topics. If you don't mind, I'll keep one chair for me, because I'm sure that I'll be around to learn a little bit more. So a little bit more personal, if you don't mind. First of all, just to, I think many of you knows the organizer. Let me just mention that we have Eric Maskin as the director of this school for many years. I just learned. I mean, and Scott Duke, commoners from Harvard, Elvin Roth, that from Stanford, that we almost lost you on the way, but you made it, so we are very happy. And Eyal Winter from the Rationality Center, who is the co-director for also many years. And of course, Kenneth, the hero, you're most welcome, and many, many distinguished guests. I'm really, really happy to have you all. Now, when a little bit, as I said, a personal note, when I stepped into this position, very interesting position, about 18 months ago, I knew very little. I wouldn't say nothing, but I knew very little about the institute itself, the Israel Institute for Advanced Studies, but I knew three things: that there is an amazing school in physics, amazing one in mathematics, and the most amazing one in economics. So really, that's all. The rest was transparent for me, that there are research group and there are conferences and there are events. And so this was kind of a common knowledge worldwide. And I think you are basically the proof that this stamp of the Israel Institute for Advanced Study is the same as it was. And I think when I say I'm from the Israel Institute for Advanced Study, I immediately say, and from the Advanced School of Economics. So people will know that we are not just a minor institute that no one heard about, but this is the real reason, and I'm very proud to say it. So my name is Michal Inyal. I'll introduce myself. I'm a biologist. I'm a molecular biologist, computational biologist, and neuroscientist in training. And I know very little about the economics, but being in the neighborhood of the Rationality Center, over the years, I learned quite a bit, and both on economics theory a little bit, and just because I decided when I stepped into this position to take only one rule, or few rules, as a matter of fact, one rule to learn everything that is said, at least one element of it. And it's a lot of fun. As you see, the next room, there is a meeting on Christianity, early days, 6th to 11th century. And so I learned about this and coming back to economic theory. But I want really to take the 1 minute to tell you something quite interesting, I think from the biological point of view, that maybe some of you didn't thought about it, but if you have a chance in the coming 10 days, you can come over and discuss it with me, which is what happened, I think, in biology in the last 10 years, or 15, but mostly the last 10 years, is really a new concept or developing concept. I think there is a lot of connectivity to what you are doing or you came to learn about, which is that the cells are not the only unit that we have to think about, but actually there is a community here. There is resource elements. There is a market, in a sense. There are small agents that are doing the job. And there are, for example, even I just want to throw some ideas, so maybe you'll keep thinking about it. So for example, cancer cells. In a sense, each cancer cells wants the best for itself, which is to divide and to produce more and more cells. However, the community of the cancer, of the tumor itself, has a lot of constraints and a lot of, so maybe the next generation of drugs will not be just a chemotherapy in which we are trying to kill the community, but instead to use your knowledge, your understanding on game theory, on decision making, on mechanism design, on market, this, and do this in order to make maybe a new thinking into the very, I would say, naive type of drugs that we are using as of today. And the field is developing also to developing single cell analysis, how different cells are behaving, so how people in the room are behaving. So there is a lot of connectivity, and we can think about it during the breaks. I don't want to take more of your time, but just if I may ask, how many of you, this is the first time for them in the IIAS? Wow. Wow. Okay, that's great. So it means that I'll say one word on IIAS. This institute was founded in 1975, way before most of you were born, I think. And indeed, the idea is very simple, to make it a place in which thinking can be stimulated. That's it. And new ideas can be planted. And our role is not to interfere. That's it. So I think that summarizes quite a lot of what we are doing. Schools, research group, conferences, events, and so on and so forth. There is only one complaint, if I may share with you. I see two little women in the room. So can all the women just stand up so we can see them? Okay. Thank you. Thank you. So this is to make as a note. You know, I'm making a list of notes for next one. So this is already one note that I made. So really, I don't want to take more of your time, but I welcome you warmly to Israel, to Jerusalem, to the IIAS, and enjoy the rest of the school. And by that, thank you again. And I want to ask Eyal to introduce the first keynote speaker, who is already introduced slightly by me, Eric Maskin, please.
Thank you, Michal. Michal suggested that I introduce the one person here that does not need introduction, which is Eric Maskin. Before that, I want to thank you all for attending this school. From what I hear from the organizer, the administrative organizer, this is supposed to be a record number. 147 students were registered. Probably not all of them are now here, but they are going to flow in. The rest are going to flow in probably tomorrow. And this is really great. I mean, seeing you here, knowing that we contribute to your advanced education is what is what makes us want to do it, actually. And Eric will do it now. Please, Eric.
Okay. I don't need that. I think I'm wired up. Can you hear me in the back? I think the microphone should be on. Okay. Well, welcome everyone. Good morning. And let me begin with some thank yous. When I decided that it would be a good time to have a summer school on matching, I thought immediately of Al Roth, and Al kindly agreed to be part of this summer's event, and furthermore, he and Scott Commoners lined up basically all the lectures. So my job was unusually simple this summer. Delegation, the delegation principle worked perfectly. So the topic, as you all know, is matching theory, and I heard a joke just yesterday, which I think is appropriate. What do you get if you match a parrot and a shark? The answer is a bird that will talk your ear off, which I think is appropriate because we, the lecturers, will be talking your ear off for the next 10 days or so. There's an intensive lecture program, but what I want to say now is that it shouldn't all be us. That is, one of the purposes of the summer school is to have interaction. So do raise questions, make comments during lectures, but equally important, talk with us during the breaks, during lunch, after lectures are over. This is supposed to be a interactive experience, so keep that in mind. Well, my job today is to give you a whirlwind sum of classical matching theory. So the results that I'll be talking about are largely old. The summer school will be concentrating on much newer results, but you need some background. So this is the background. So what is distinctive about matching? Of course, a lot of economics is exchanges between buyers and sellers. It's not at all unusual to look at markets where the sellers are heterogeneous, by which I mean that they each sell different goods, and buyers will not be indifferent among these different goods. I think what's distinctive about matching markets is that in addition to buyers caring about which seller they buy from, the sellers care about which buyers they sell to. So a familiar example of this is think of a market for education. The prospective buyers here are the students. The sellers are the schools or universities. Clearly, students will have preferences over schools, but also it's commonplace that schools will have preferences over students. They will view some students as more desirable than others. So that's the sort of situation that matching theory applies to. Now there's another more technical feature of matching theory which often comes up, which is that it's typically a world with indivisibilities. So in most circumstances, a student will attend exactly one school, not a fraction of a school, so that there are some built-in indivisibilities in the model which have to be taken account of. Well, what I'm going to do now is to set up a matching model. It will be a particular matching model that other lecturers will elaborate on in the course of the school. This is going to be a model in which there are two sides. Actually, but before I get to the model, why don't I discuss what I would call the three sides of matching theory. There are essentially three things that matching theorists try to do. First, there's the positive side of the story. In this case, we might try to predict which buyers are going to be matched with which sellers, and in equilibrium, what prices prevail. But then we can look at things from a normative perspective. We might ask which matchings between buyers and sellers will have the desirable properties we might seek, such as stability or fairness. And then third, we might be interested in how we can find such desirable matchings. And so this is the mechanism design or market design or algorithmic part of the story. And the school will look at all three sides. We'll put particular emphasis, I think it's fair to say, on the second and third. So we're not going to be looking so much at competitive equilibrium, but in the talk I'm giving tomorrow, which is trying to draw a connection between matching and inequality, I'll be firmly in the first side, that is the positive side. Okay, so now let me turn to the model. In this model, there's a set of sellers. Each seller has a single indivisible good for sale. There's a set of buyers. Each buyer wants to buy at most one good. So we're looking at what's called a one-to-one matching model. A buyer is matched with at least one, with at most one seller, and vice versa. In later lectures, this model will be elaborated. We will look at many-to-one matching. So it may be the case that each student is assigned to one school, but schools can be assigned many students. There'll be a certain amount of focus on many-to-many matchings, where hospitals have many doctors, but a given doctor could be working for multiple hospitals. So we'll suppose that each buyer eyes utility, each buyer eyes payoff, depends on the seller with whom he's matched. So let ui of j be the utility buyer I gets from obtaining seller j's good, being matched with seller j. And this could be a positive or negative number. What I'm going to do is normalize both the buyer and seller's utilities of being unmatched to 0. So if a seller is matched with a 0 buyer, then that's being unmatched, and that generates a utility of 0. Each seller gets a utility Vj of I from selling to buyer I. And this number Vj of I could include the cost of providing the good to buyer I. I think I switched the subscripts here. This should be V sub j of I. So, as I said, this is a one-to-one matching model. It's also what's called a two-sided matching model, in that there are two distinct populations. There are buyers and there are sellers. They are different populations. We could also look at, and there's a large literature on this, at one-sided matching, that is, where there's a single population from which matches are made. So there's a classic problem called the roommate problem, where we have a population of people who are going to be paired up as roommates, or there's the house assignment problem, where each person has a house, but might prefer other people's houses. And so the question there is how to reallocate the houses in a desirable way. I'm not going to be looking at that today, but you will see that later on. Let me start, although this will not be the main focus of this lecture, on the case where there's a perfectly transferable good, where there's money. And in this case, we can talk about prices. Pij is the price that buyer I pays for seller J's good. And because we're not saying anything about the sign of the utilities, Pij could be positive or negative. So buyer I's payoff will be his utility from being matched with J minus the price he pays. And seller's payoff from being matched with buyer I is Pij plus the utility he gets from being matched with I. So we can describe an allocation, a matching, by a matrix, Xij, for all I and j. Xij is 1 if buyer I and seller j transact, if they are matched. Xij is 0 if they're not matched. And because we're talking about being unmatched as being either the 0th buyer or the 0th seller, it'll be the case that for each buyer I, the sum of the xi j primes over j prime will equal 1, and similarly for each seller j. In other words, each buyer is matched with one and only one seller, and each seller is matched with one and only one buyer. So in this setting, a competitive equilibrium is just a matching and a corresponding matrix of prices such that each buyer is maximizing, each seller is maximizing, and the amount that buyers and sellers demand itself matches. Supply equals demand. The first observation is that in a setting like this, we get a competitive equilibrium, and it is essentially unique. I'll explain what I mean by that in a minute. The only notable thing about this claim is that we get existence despite the non-convexities that are created by these indivisible goods. Let me explain how technically we can get around the indivisibilities. Yes? Yes, thank you. Yes, these should be pluses. Right.
Literature that takes into account when you set the utility function, you take only into account affecting the utility whether there is a match. And my question is whether the other possibilities that they are not matched affect the utility. What makes me think about this is the well-known example of the menu theory, when you have fish and meat and meat and chicken, and you have the third option that you won't choose anyway, but it affects your utility. I mean, The question is whether the other possibilities that I do not choose do affect, and I don't know, I'm not going to be matched, but I still there available for a reason. I don't get too much to them. Do they affect my utility?
In this framework, they don't. We're assuming that your utility depends only on the seller that you are matched with, and the ones that you aren't matched with don't affect your utility. But there are cases where the extension to the externalities like that would be reasonable. Yeah. You know, this is really a bare bones model, and there are elaborations in many directions that have been examined or could be examined. Yeah, by the way, all the lectures, if lecturers agree, will be posted on the websites. Mine will be posted, and I will correct the typos. So in particular, these will turn out to be pluses in the corrected version. So competitive equilibrium exists and is essentially unique. Now, to convexify, the problem technically is that demand by buyers for houses isn't so well behaved. With a small change in prices, a buyer might switch from one seller to another. But we can make things nice and convex and continuous by imagining that buyers randomize over sellers. That will make the demand correspondences well behaved. They will be upper hemi-continuous and convex valued. We can do the same thing for sellers, make their supply correspondences upper hemi-continuous and convex valued by allowing them to randomize. And then we get an equilibrium. Now, it will turn out that with probability 1, no randomness will actually occur in equilibrium because, as you'll see in a minute or two, in equilibrium, there is a unique, essentially unique possible matching, which itself is not random. But even in the case where there is randomization in equilibrium, we can always convert it into a non-random equilibrium. So here's what I have in mind. Suppose that there are two buyers, I and I prime, two sellers, J and J prime, and in equilibrium, they are assigned in a random way. So I is assigned to J with 2/3 probability, I is assigned to J prime with 1/3 probability. Well, we can convert this into a non-random equilibrium, which is welfare equivalent to the random one. We can convert this into an equilibrium where I is assigned to J with probability 1, I prime is assigned to J prime with probability 1. All agents are indifferent between this and this, and we can always do this. It's a simple argument to show that we can always go from the random allocation to the non-random one. So there's no, although we use randomization as a technical tool to show that there is an equilibrium, then we can get rid of the randomization. Now, for each matching, the corresponding set of possible payoffs is going to be a hyperplane. We're assuming quasi-linear utility, and so for each if this is utility space, for each matching, we can get all payoffs along the 45-degree line through that point by making monetary transfers. And therefore, each matching corresponds to one of these hyperplanes. The best matching is just the matching that gets us onto the highest hyperplane. And that's the matching that solves this problem. We look for a matching which maximizes the sum of utilities. And at least generically, there will be a unique solution to that optimization. And so generically, there will be a unique equilibrium matching. There could, because of the indivisibilities, be multiple prices, however, sustaining that same allocation. So it's the allocation rather than the prices that are unique. Question, where's the question? Over here. Sorry.
So you just spoke of the allocation as a hyperplane. Could you specify in what space that is a hyperplane?
In utility space. So the matching gives rise to utilities, but then we can, by making transfers, we can get all other utility vectors in that hyper. That's right. That's right. The sum of utilities will add up to a constant. Now, one of the major themes of matching theory is to look at which matchings are in the core, or which matchings are stable. It's worth pointing out that that there is, as usual, a strong connection between the core and competitive equilibrium in this model. What do we mean by a matching being in the core? Well, a matching together with monetary transfers is in the core if there's no coalition of buyers and sellers that can block it. That means that there's no group of buyers together with sellers who can make transfers among themselves, transfers that add up to zero, and reallocate the goods among themselves, the goods that their coalition have among themselves, so that each buyer is strictly better off and each seller is strictly better off. If there were such a coalition, we would say that the coalition blocks the matching with the transfers. A point is in the core if there is no blocking coalition. I'm going through this quickly because I imagine all of you have seen the concept of the core at some previous point. Well, as usual, a competitive equilibrium is in the core, and I won't go through the argument. It's standard arguments, but you can find it on the slides if you want to see the details. We also have, for this model, an even tighter connection between the core and competitive equilibrium than usual. That is, not only is every competitive equilibrium in the core, but any core point is a competitive equilibrium. And this follows from, essentially from the uniqueness of the core, just as there is a unique competitive equilibrium matching, there is a unique core matching. If the core matching did not maximize the sum of utilities, then the coalition of everybody could make everybody strictly better off by moving to a different matching. So I will skip the details of why the core is in the competitive equilibrium, but it's essentially because of this uniqueness property that I just mentioned. Yeah, yes. Hi.
Regarding the weather result, I want to see if I stretch it to the weather result. I don't want to stretch it too much, but if I think about the market in the context of men and women, let's say men can pay women have matching, then it seems that the result says that the equilibrium that you get here is even better to men than the famous stable equilibrium where men ask women, when matching starts with men, right? Because the regular, when you don't have prices, you have the stable equilibrium where men offer women.
Yeah, I'm coming to that.
Prices are zero, right? So you don't pay them. But now you can pay them and you get something that is
Well, actually, so I haven't said whether prices are positive or negative here. We're allowing for.
some women will buy.
It really all depends on the relative magnitudes of the utilities. It could be that the women will be paying negative prices.
Some will pay.
Yeah,
Some
yeah, yeah. So no clear-cut welfare comparison. I want to make one more observation before moving on to the case where we drop prices. And that's on assortative matching. Let's look at the special case of the model that I've been talking about, in which buyers and sellers' indices reflect their productivity. So the higher the buyer's index, the more productive is the buyer, and similarly for the seller. And here we're talking about productivity as the in terms of the sum of the buyer's and the seller's utility. So Wij is the total product of buyer I and seller J. Now suppose that it's the case that a buyer's marginal productivity is increasing in the seller's productivity and vice versa. So in other words, the advantage I have from being a productive buyer is magnified if I'm matched with a more productive seller. This is a restrictive assumption, but it's an assumption which holds naturally in many applications, in particular in the application to inequality that I'm going to be talking about tomorrow. So this is the assumption we're making. Well, the main qualitative conclusion I want to draw from this is that if we make this assumption, assumption 11, then in equilibrium, in competitive equilibrium, there will be what's called positive assortative matching, in the sense that higher quality or higher, more highly productive buyers will be matched with more highly productive sellers, and vice versa. And I could go over the proof, but I think, once again, I will leave that to your post-lecture study. It's just a couple of lines. So this is all I propose to say on the case where there is money or some sort of transferable good that can be used as money, the rest of this morning's talk will be on the case where we drop money from the model. Michael.
I want to come back to your definition of the call.
Yes.
You have no blocking
Right.
coalition. And in the blocking coalition, you had a condition that all buyers and all sellers, if they move, increase their utility.
Right.
Now, suppose that you have a group of buyer sellers and you matching, well, some increase, some buyers, some sellers increase, but not all, and then they make side payments to those who didn't increase, so that altogether it's now with a side
Yeah.
payments,
Yeah.
it's in their advantage to block.
That's right. So the definition.
I felt that the definition was a little bit too limited.
Well, the side payments are included. These are transfers, monetary transfers. So we talk about a core as a matching together with transfers, which might include side payments. Yeah. Okay, so let me drop money from the model, which seems appropriate for many settings of buying and selling. If we're talking about public schools, for example, we don't think of students buying seats in a public school, nor do we think of the public school as selling seats, although there's some of both in reality, but limited.
There are competitors to public schools where there is buying and selling.
That's right. But let's look at the market for public schools in isolation. Now we no longer talk about competitive equilibrium because we no longer have prices. So the allocation has to be done some other way, and that's what I want to discuss. We can still talk about a core. A core is the exact analog of what I was discussing before. A matching is in the core if there don't exist if coalitions that can block. And by blocking, we now don't have side payments anymore because it's assumed there's no money to make side payments. The allocation is blocked if for every buyer in the blocking coalition, there is a seller in the blocking coalition that the buyer prefers to the proposed matching, and vice versa. So a simpler way of putting this, since all matching is bilateral, a simple way of expressing the core is that it consists of all matchings in which buyers and sellers, first of all, are getting non-negative utility. They can always remain unmatched if they prefer. And furthermore, for each buyer, there does not exist some other seller J prime, that is a seller to whom he's not matched, for which these inequalities hold. In other words, the buyer would rather be matched with this seller, J prime, and the seller would rather be matched with this buyer than the buyer with whom he is matched in the starting matching. So we can look at the core in terms of these deviations by a single pair of a buyer and a seller. Now, we no longer have competitive equilibrium, so we don't have the same core existence theorem that we had in the case we saw before, but we do have a classic result by Gale and Shapley showing that the core is non-empty, that there always exists what is called a stable matching. A stable matching is just a matching in the core. And one nice thing about this demonstration is that Gale and Shapley propose a simple algorithm that can be followed to get us to a stable matching. And here's a version of that algorithm. It's a multi-stage algorithm, and at any point, some of the buyers are currently matched with other sellers. Matchings, by the way, are all tentative or provisional until the ending. So at any stage, it's only the buyers who are currently unmatched who do anything. Let's arbitrarily choose some order of buyers. It will turn out that the order of the buyers doesn't matter, and we'll see that in a few minutes. But let's choose an order in which buyers, in turn, get to make proposals to sellers. So this is what is called the buyer proposal version of the Gale-Shapley algorithm. Each buyer who is not currently matched will go to his favorite seller, the seller who gives him the highest utility among those sellers who have not already rejected him. And what do I mean by rejection? Well, if buyer I makes a proposal to seller J, and J prefers I to the buyer that she's currently matched with, she'll reject her current match, I prime, and replace that match with I. But otherwise, she'll stick with I prime and reject I. So this is the key feature of the algorithm. The seller, notice that the seller's utility must be increasing over time because she only replaces old matches with new matches if the new matches give her higher utility. And the algorithm ends when each unmatched buyer has been rejected by all the sellers which would give him positive utility. So those buyers remain unmatched, and all of the ones who are currently matched get those matches. So that's the algorithm, and the next step is to see that it actually delivers a stable matching. Any questions about the rules? By the way, it's called the deferred acceptance algorithm because, as I mentioned, matchings are provisional, where sellers' acceptance of buyers is only provisional. We have to wait until the end to see who actually does get matched with the seller. So why does this algorithm work? First, there's only a finite number of buyers and sellers, so the algorithm will terminate after a finite number of stages. Why does it terminate in a stable matching? Well, suppose it didn't. That is, suppose it resulted in a matching xij. But suppose that, that for some buyer I, there was another seller, J prime, with whom he would prefer to be matched. So J prime gives him higher utility, and furthermore, J prime would rather be matched with I than with the buyer that she's supposed to be matched with. Well, notice that buyer I must have proposed to J prime at some point in the algorithm, because remember, buyers propose in decreasing utility order to sellers. If the buyer ends up with this utility, that means he must have been rejected by all sellers giving him more utility. So he must have been rejected previously by J prime. But that's impossible, because from 13, J prime actually prefers I to the buyer that she ends up with. And remember, sellers' utilities must be increasing over time, so the seller can't end up with this low utility when she could have had this higher utility. So in other words, there is no blocking pair. Yeah.
Is it important to the result that both of the inequalities are strict versus one strict and another non?
Yes. In this case, we require strict inequality. We don't, I should add, at this point, we do not require that preferences be strict. That is, this argument does not rely on sellers never being indifferent between two buyers. In a little while, I'm going to impose strictness of preferences to get some further results. But for existence of a stable matching in this sense, we don't need that assumption on preferences. Okay, so now we've shown that a stable matching exists. I've looked at the case where buyers are making the proposals. That's called the buyer proposal algorithm. We could do exactly the same thing for the sellers. And first point I want to make is that we might get a different matching. Now, when there was money around, that was not the case. There was essentially a unique matching in the core found by maximizing the sum of utilities. But now it's without money, there can be multiple core allocations, multiple stable allocations. Here's a little example. This is an example with two buyers, I and I prime, two sellers, J and J prime. Notice that I likes J best, I prime likes J prime best. If the buyers are making the proposals, I will be matched with J. I prime will be matched with J prime. J and J prime are happy with that because they do better than remaining unmatched. But if the sellers are making the proposals, we'll have the opposite sort of matching. J will be matched with I prime. J prime will be matched with I. So who makes the proposals matters here. And now I want to make this additional assumption about preferences, that both buyers and sellers have strict preferences, meaning that they're never indifferent between two people on the other side of the market. And I want to establish two things. Let's go back to the buyer proposal algorithm that I started with. And I fixed an order of buyers who in turn are making proposals. The first claim is that it doesn't matter what the order is. The ultimate matching will be the same. And second, the matching will be optimal from the point of view of the buyers, in the sense that each buyer will at least weakly prefer the matching from the buyer proposal algorithm to any other possible stable matching. When I say weakly preferred, he might have the same matching, the same match in some other stable allocation, but he can't do strictly better off in he can't be strictly better off in any other stable matching. Well, the proof of this claim is once again very simple. Let's go through it. Suppose that for a given buyer I star, we'll call seller J star possible for I star if there is some stable matching where I star and J star are matched. Now let's go through the buyer proposal algorithm, and we'll fix some order of buyers. And suppose it's the case that before stage S occurs, no buyer is ever rejected by a seller who is possible for that buyer. But suppose that at stage S, I star is rejected by seller J star, even though there is some stable matching where the two are matched. What I want to argue is that this is actually an impossibility, that in the buyer proposal algorithm, a buyer will never be rejected will never have a proposal rejected by a seller for whom that buyer is possible, or the seller is possible for the buyer. So, but suppose I star were rejected by J star. That means that J star, in order for J star to reject I star, J star must have received a better proposal, say from I prime. So we have this inequality, which says that J star's utility from I prime is better than the utility that she gets from I star, the buyer who's being rejected. Now, I prime has not been rejected in any of his previous offers to sellers, because by assumption, I star is the first buyer who is ever rejected by a possible seller. So J star, I prime must prefer J star to any seller, J prime, who is possible for I prime. But that means that I prime and J star together block the matching that results from the buyer proposal algorithm, because each of them is doing better than in the buyer proposal final matching, which means that our assumption that I star is rejected by a seller that's possible for I star must have been false. And that means that buyers are never rejected by sellers who are possible for them. And that means that since buyers get to make the proposals in any buyer proposal algorithm, that is, for any order of the buyers, a buyer must end up being matched with his favorite possible seller. And that completes the argument. Are there any questions about why these claims are true? So now we can talk about the buyer proposal stable matching. It doesn't depend on the order of the buyers. And we can also talk about the seller proposal stable matching, which I will denote using a superscript S. And exactly symmetrically, all the sellers will weakly prefer this matching to any other stable matching. The next thing I want to discuss is strategic issues. So let's go back to the buyer proposal algorithm and imagine that that agents are submitting their preferences, their utility functions or their rankings to a central clearinghouse, and the clearinghouse determines what the matching is on the basis of those submitted preferences. Would a buyer ever gain from submitting a false ranking? And I'd like to argue that the answer to that is no. Remember, looking at the buyer proposal algorithm at the moment, sellers will in general have an incentive to misrepresent, but not buyers. And I'm not going to give the complete argument, but I'll give you one half the argument and let you read the second half on your own. So suppose that some buyer I star actually gained by submitting false preferences. That means that I star is inducing a different matching, we'll call it Xij star, from the buyer proposal stable matching Xij_B. Now we know that this is a stable matching with respect to the submitted preferences. That's Gale-Shapley. But what we want to argue is that this matching can be blocked by agents other than I star if this matching differs from this one. And therefore, that will contradict stability, because if this matching can be blocked by agents other than I star, notice that the other agent's preferences are the same. We're only contemplating changing I star's preferences. And so if the other agents can block this matching, then if the other agents can block this this matching with true preferences, then they can block it with I star's false preferences, contradicting Gale-Shapley. That was. Let me make sure everyone's with me. It's a slightly subtle point. Are there any questions about what I just said? Or yes.
Does everyone knows everyone's preferences? Is the information like available to all? Is there a common knowledge?
Yes. Let's suppose that there's common knowledge
About what?
about preferences.
So it's known that the preferences are false. Other people know that false preferences have been submitted.
Yes, actually, that point is not important. But let's suppose that everybody knows everybody's true preferences.
Oh.
This is stronger than necessary for the argument, but I think it makes the argument more transparent. Let me say this again. I'm going to show that this matching that I star induces can be blocked by agents other than I star when for the true preferences. Everybody knows I star's true preferences. But since the agents doing the blocking have the same preferences in both cases, for the true preferences, false preferences, that means that they can also block this allocation for the false preferences, which violates the general argument that the Gale-Shapley algorithm generates a stable matching. So that's the key to this argument. So to show that, let's first of all look at the set of buyers who prefer the starred matching to the matching that you get with true preferences. So that's B star. And let S star be the sellers who are matched with the B star buyers in the starred matching. Let me use the notation S star B to denote the sellers who are matched with the B star buyers in the matching that arises from true preferences. This set S star B may not be the same as S star. In fact, I want I want to consider the case where they're not the same. That's the only case that I'm going to look at. I will leave the rest to you. So let's suppose that these sets differ. That means that there must be some seller in S star who is not in S star B. That is, there is some seller who is matched with the buyers who prefer the starred matching in that starred matching and are not matched with the buyers who prefer the starred matching in the original matching. Sorry?
Who is J prime?
Yeah, that's. I think I just want to check. I think I might have eliminated from the slide who J prime is. Yeah, I'm sorry. This should be J prime. So we're choosing J prime such that J prime is in S star but not in S star B. Somehow the prime got eliminated in the most recent match. So let's suppose so J star has to be matched with somebody in B star. Notice that everybody in B star is matched with a seller. That no one in B star can be left unmatched because everybody in B star prefers the starred matching, strictly prefers the starred matching to this matching. So they must be matched with some seller. So since J star is one of the sellers in S star, J star must be matched with some buyer in B star. And that means, by definition of B star, that buyer I star prefers J star to the matching he gets when he's truthful. Sorry, in the match where everyone is truthful. Now, if J star also preferred I star to all possible buyers, then I star, J star would block. So it must be the case that there is some other buyer, I double star, whom J star prefers to I star. Otherwise, we have an immediate contradiction. Now, I double prime is not in B star because J star is not in the set of sellers who are matched with members of B star. Since J star is matched with I double star, that means that not I double star, I double prime is not in B star. But that means that I double prime must prefer J prime to the seller he's matched with in the starred allocation. Remember, I double prime is not in B star. So that means that he prefers the B allocation to the starred allocation. So he's matched with J prime in the B allocation. He prefers that to J double prime. But that now then implies that I double prime J prime block the starred allocation. And therefore, the starred allocation cannot have been generated by the Gale-Shapley algorithm, because the Gale-Shapley algorithm only generates stable allocations. Okay. This is probably the most convoluted argument that I'm presenting today, so you may want to review it, but it's short. Yeah.
I have a historical question.
Yes.
Did Gale-Shapley consider the possibility of false preferences and rule them out? In other words, is
Yeah.
that argument already in Gale-Shapley?
This argument is not in Gale-Shapley. I believe that Al Roth back there, together with Dubins and Friedman, were the first to look at this kind of argument. But Al, if Al is listening, perhaps he can correct me. This result is essentially due to you and to Dubins and Friedman. Is that right? Okay. Yeah. So so we've now shown that in the buyer proposal algorithm, buyers are going to be truthful. It turns out that essentially the same argument also shows that if we fix preferences and we look at different stable matchings, remember there are multiple stable matchings in general possible for the same preferences. If we in different matchings, different sellers may be paired with different buyers. However, the same set of buyers and sellers will be matched in any stable matching. And I'm not going to show you the complete proof, but let me show you enough of the proof so that you'll see that it's essentially the same as this slide. So here is the claim. Can people over on this side see the board here? Maybe not. I'll read it out. Okay, you can check later. So if I'll read it out while I'm writing it down. If a buyer is matched in some stable matching, then he is matched in all stable matchings.
All what?
All stable matchings. And the same thing for sellers. And here's the proof. Suppose that were not the case. Suppose that I star is matched in stable matching xij star, but not in stable matching Xij B. Now repeat the argument on this slide, and we'll get exactly the same contradiction that we got on this slide. So that's a useful thing to know. I'm skipping over the rest of the strategy proofness arguments, but it's there on the slide for you to check later. So we've seen that it's in effect a dominant strategy for buyers to be truthful in the buyer proposal algorithm. Now, what about sellers? We're using the buyer proposal algorithm. Will sellers gain from revealing their true preferences? Not necessarily. And the same example we looked at before shows why that's the case. So here again we have two buyers, two sellers. If the buyers are making the proposal, I will be matched with J, I prime will be matched with J prime. But suppose that J instead of submitting her true ranking, which is I prime I 0, moves 0 up to the second spot. In other words, J is saying that she would never want to be matched with I. That's worse than being unmatched at all. Well, then that means that J is going to have to be matched with I prime. That's the only possibility. And that will be stable. So that's fine. But it's not the matching that would have resulted had everyone been truthful. So that shows that buyers, although buyers are going to be truthful, sellers in general have an incentive to manipulate. However, the scope of their manipulation will be limited. And let me write down one more result that I didn't. That I didn't have a chance to get onto the slides. So I promised I wasn't going to erase this statement, so I'm going to have to erase.
You can push that in and you'll have a little.
Oh, that's true. Okay. Very good. Very clever. So the claim is that when submitting false preferences, it suffices for a seller to truncate. And by that I mean the only thing that's going to be manipulated is that the 0 points might be moved up. The ranking will remain exactly the same. The false ranking will be exactly the same as the true ranking. However, the seller is making the claim that fewer buyers are satisfactory than is actually the case. And given what we've already seen, the proof of this claim is extremely simple. Suppose it were the case that a seller gained from some manipulation. Now I claim that manipulation must be a stable matching with respect to the true preferences. Why is that? Well, suppose that it were not stable with respect to the true preferences. Well, that matching would also be attainable by the seller in the seller proposal algorithm. And we already showed that in the seller proposal algorithm, seller never gains from being untruthful. So it can't be the case that an impossible matching, a matching that is not possible for seller J, could be an outcome of a manipulation by the seller when the buyers are making a proposal. Yes?
It's actually the precise claim is that if a seller manipulates in an optimal manner, in a sense
Right.
that they cannot manipulate any better, then
That-
the resulting stable is matching.
That's right.
If a seller manipulates in a way that improves her outcome, but is not an optimal manipulation for that seller, then that may be unstable.
That might be unstable, that's right. So I'm only talking about optimal manipulations.